All right. How does that look?
Yeah, looks fine. Go ahead.
All right. Okay. Hi, everyone. I'm Kevin Hernandez. I'm going to be presenting and teaching you guys about my personal research topic, high-speed store separation. So just an overview, what we're going to go over today is I'm going to introduce you all into cavity flows, introduce you into store separation, go over some of the existing research and its findings, and then just a little bit at the end, go over my personal research and what I'm doing, and then a summary at the end. So for cavity flows, Duval in our class actually gave a great presentation the other week on it. So we're in Dr. Kumar's group, and a lot of us are doing research very similar and very intertwined into cavity flow and store separation. So I'm going to go just briefly into this, just on the general aspects and just how it pertains to store separation. So to start, what are cavity flows? Cavity flows occur when a fluid passes over a recessed or hollow region on a body, on a vehicle, and they generate these complex flow fields that include some flow features like shear layers. They create acoustic resonance, recirculating zones, and some common examples. Here in this figure, I have a truck where the bed is a cavity on it, and it's just a nice flow simulation of it. And then in more of our context, we look into aircraft. So the aircraft landing gear, when that landing gear door opens, that creates a cavity on the vehicle. And then in my research context, the aircraft bays. All right, so now for some context. Cavity flow research, it dates back to the 1950s and 60s. Notably, Rossiter, he made a lot of progress in this work. His research explored the acoustic modes created within the cavity, and he found and created a semi-empirical formula where you're able to predict the modes created by a given cavity depending on the flow conditions and that cavity geometry. So now for supersonic cavity flow, it creates a lot of potential problems with the system. So firstly, it induces drag onto a vehicle, and then it creates this highly unsteady and turbulent flow system. And at the bottom, we have a diagram here of the cavity flow, and I'm going to go over it more in depth a bit later. So now, as we talk about store separation, we're going to be talking about cavities in the context of this aircraft bay. And now, before we jump into that, hopefully this works. I think Duval might have also showed something similar, but these are also, these are really cool videos. So these are some videos of store separation, as the title says, incidents, just where store separation doesn't go right, and just kind of shows you firsthand of the potential dangers of this system. So, and just for context, you'll see in these videos that they're just stores attached to the outside of the aircraft. These are older videos, but not within the cavity. But just to give you a general idea. So one of the main dangers is the store releasing from the parent aircraft and then coming back up, not being able to, go where it wants to due to the unstable flow system, flow field, and then hitting the parent aircraft back. All right. So now, what is store separation? So store separation, it refers to the process in which an object, which we call the store, is released from a parent vehicle, and it creates a complex problem where we have to look at the aerodynamic, inertial, and potentially propulsion forces on the store to determine its trajectory. And when understanding, or we aim to understand these factors so we can have a stable and safe release. So why do we want to look at store separation from within a cavity? Well, as technology improves, actually, I'm going to refer to the figure on the slide here. So as technology improves, we have our electronics and devices. They take up less and less space. And instead of just completely redesigning the aircraft, making it smaller, it's already well understood. We have more space. And within that space, we can fit more things, such as the stores, which are once stored or once held on the outside of the aircraft. Now we can bring it inside. And this helps, namely by number one, reducing drag. That's easy. And secondly, it increases the safety of that store during the flight phases, as it's not subjected to the outside flow conditions, making it safer for the pilot. Now, what are the challenges here? Well, successful store separation involves understanding all of these properties and forces surrounding the store and cavity flow system. And it's been shown that the cavity flow system has strong effect on these stores, and as we saw in the last video, has potentially detrimental effects on it. Okay, so now bear with me as we're going to walk through and go over each of these flow features in the cavity system and how they interact with one another and as a store as it's being released. So in this figure, we display the key features of the cavity flow diagram. So first we have the incoming turbulent boundary layer. And now in our context, this is going to be coming from the underside of that parent aircraft. Next, we have that boundary layer separating over the cavity and creating this shear layer. It contains large and small instabilities, and is created as it goes over that leading edge. And now as that shear layer moves down the cavity, eventually it's going to hit the rear wall. And at this point, we're going to get what we call the acoustic source, where now this shear layer is going to hit, and that flow inside is actually going to create a feedback loop that goes back and forth, and we get these acoustic tones that are created. And this is what the previous work and formulas, aim to do and predict these tones. So now, and then the final feature, we have the leading edge shockwave, which is just created from the lip of the cavity. So when we implement a store here, that store, when it's separated, it has to go through all of these different flow features, all these potential problems to be released. It has to go through this feedback, internal feedback within the cavity. It has to go through that shear layer where we have a significant velocity gradient. I mean, there's a rapid change of velocity from the subsonic cavity to the supersonic flow outside, and then past that leading edge shockwave. So now for the research, the overall research objectives surrounding this problem. Firstly, we want to characterize the high-speed cavity flow, understand it as best as we can, and do that using different techniques, qualitative, quantitative techniques. Then investigate the store separation dynamics at some subsonic, supersonic, hypersonic conditions, and understand that as best as we can. And finally, which is my research angle, which is investigating the effect of multiple stores releasing from within the cavity. So now just to go over some of the research findings, recent research findings so far. And we have a figure here with how we conduct our research here at the COE and the AME building and the FCAP wing and the polysonic wind tunnel. So this is a cavity model that is recessed into our wind tunnel, and we have two stores that are mounted to it, and here we study it. All right. So some of the findings we have here. So firstly, it was found that the location of the store in the location of the store highly influences the flow field of the internal cavity. And when we have the store blocking some of that cavity internal volume, it disrupts the feedback loops and weakens that resonance, making it potentially safer for these stores releasing. It was also found that the cavity resonance, the maximum reduction seen is when the store is partially protruding from the cavity and is right on that shear layer that we saw in that prior diagram. And now looking at the difference of a single versus a pair of stores, well, we actually see that, a single store reduces the cavity frequency, but the pair of stores further increases that at supersonic speeds, and it offers the greatest reduction. And it actually was found that the two stores implemented reduces the those peak tones, the amplitudes, by a significant amount. However, even though these studies have showed reduced cavity resonance, the suppression was only partial, leading this environment to still be somewhat unsafe for the stores that need to be released. And now I'm just going to walk us through some of the research that's been done and some of the research that I'm doing to better understand this problem. So first, we have one technique that we use, force balance testing. There's a force balance device within a store here that we see in this diagram that collects force and moment data and gives us a 6-degree understanding of what this store is experiencing in flight. And we use what we call the CTS, Captive Trajectory System. That's a device that we mount inside our wind tunnel, and actually gives us the ability to move that store mid-test in different directions inside the wind tunnel. So what we do with that is, in this figure here, we have the store mounted onto the CTS and looking at, starting from A, B, C, going down, you can see that the store slowly moves down to different vertical location within the tunnel. And what we're doing here is we are capturing the moment and force data on that store at these different locations, vertical locations, streamwise, horizontal locations, and at different pitch angles. And with that, we're able to get a complete force and moment database. And this allows us to potentially create some trajectory simulations that simulate how the store is going to be released. So now finally, for my personal research, sorry, I think my my voice is going out a bit. But for my personal research, I'm looking at this multiple store release. And this is just a simple diagram to give you an understanding of what I'm looking at, which is the flow coming off of two stores, interacting with each other and then interacting with the stores. So it creates a complex flow field. So in my approach, we're simplifying and breaking up the problem. So in the end, I want one of my future research tunnel installations is going to be looking at actually just two stores mounted within the tunnel and looking at how they interact with one another. So, but first, I essentially created shock generator models, which we can essentially call 2D stores, where instead of a conical shock coming off of the store, it's only just a planar shock. And here, it's very fundamental, and just studying the interaction between these shocks, which we can later, extrapolate to the 3D flow of the conical stores later on. So here's some mean shadow graph I took. And then in this experiment, I also performed PIV. And here's a little overlay of the PIV results onto that shadow graph. And then this is just more in depth of that PIV image. So here I have 2 shock generators that are each have a wedge turn angle of 10 degrees, turn angle into the flow, creating a resulting shock. And I studied different wedge angles at different Mach numbers to get a big database of, to later compare to these stores, which are going to be at different pitch angles and looking at different Mach numbers. And here's the PIV results again. And then, so for final summary and conclusion, cavity flows they're these highly complex flow systems. And with that, we find that store separation is very difficult and can be a really dangerous process. So for the ongoing research effort of store separation, where we're characterizing the cavity, and we're collecting as much valuable data of this store separation problem to eventually have hopefully a full, complete understanding to make it safer in the future. And then my personal research is going to investigate multiple stores releasing and how those affect one another. All right, that's all. Thank you.
Okay, thank you, Kevin. So let's see if you have any question for Kevin. Anyone?
Yeah,
Okay.
I have a question. Can you all hear me?
Sure.
Yes.
Yeah, so in industry, actually encountered this problem, and the tolerances between the missile and the cavity are like very small. And there's actually like a lot of autopilot issues when you're patching from the aircraft. It just can't really handle it. And I wanted to ask, is there a way to like predict these cavity flows so that the missile can like counteract the turbulence from the shock waves as it releases?
Okay. Awesome question. So I'm still learning about this problem here. From what I can tell you from my understanding, so here I kind of talked about. So you say predict the cavity flow. I don't have an answer for that exactly, but what we are doing is we're looking at a specific cavity geometry, a specific length, depth, and width cavity, and collecting all this force and moment data, and these, I guess, in a way, these trajectory simulations that we can make from that predict how the store is going to release from the cavity, this specific cavity, given different initial conditions that we can set it to. So from my understanding, that I don't know about predicting the cavity flow itself. We understand it a good deal, but given a specific cavity, we can predict how the store is going to be released.
Okay, thank you.
Okay. Anybody has a question? Okay, then thank you, Kevin. Good presentation.